This is going to be a video on me attempting to explain what learning vector quantizers are to somebody who has never heard of them before and has some basic understanding of just math, I suppose. Essentially, first things first, actually, I should say, I am not a professor, I don't have a degree or anything just yet, I am still a student, but I figured maybe because I am still a student and I have that understanding, maybe I can convey it in a student's eyes to make you understand it. So first things first though, what are learning vector quantizers? Well, in the world of unsupervised machine learning, they are a clustering algorithm. And what they aim to do is they aim to divide a large number of inputs into smaller defined groups. So converting 100,000 inputs to, say, one group of these, another group of these, and another group of those. And it does this by having a single node represent each of those groups. So to illustrate this, I'll have a little example here. Who doesn't love a good little graph here? So you can see here we have two inputs, an x and a y. Think of this as maybe, your weight on the x-axis and your height in the y-axis. And we have 9 points here, the little dots, 4 over here, and 6 up here on the top. And we can all very clearly see with our eyes that there is definitely some sort of grouping between them, right? We can see that there is a group that should be formed over here, and another group that should be formed up here. So that, let's say we have a new unknown point, also they are color-coded, so let's say that the greens are maybe girls and the reds are guys. If we find a new point that has this x value, so this weight and this height, they are in the region of the guys, so most likely they are a guy as well. That is very simple though. And we can illustrate all of what I just said using some notation. Using that here on the left there. So the inputs are essentially your descriptive features, that is your weight and your height. And your possible outputs are the sort of groups that they might fall into, such as your guys or girls, or red and blue, or green, I suppose. Just ignore the fact that I said blue here, but they're green over there. And these two blocks here are what we are going to try and use to represent these groups. They are the representative nodes. And what they have are weights. These weights are effectively like the inputs. They describe where they are in the space. The end goal will be to try and move these two nodes over the groups so that they are exactly like what we saw earlier, where we can visualize a little circle around the different groups. Now, the way it does this is initially these nodes are placed randomly. Sometimes maybe you place them at a specific point, but as you can see right now, they are very bad examples. They don't really describe the groups at all. Now, what we do though is after we place them initially, I will have some example here. Here's where the math comes in, but again, this is going to be some math, but it's going to be very basic math. You don't have to worry, we're not going to do any complex calculations and stuff like that, right? But also the main point about why we are using learning vector quantizers is that, again, we can see these things very clearly. We can see that there should be a grouping around these nodes here and above here in this 2D axis. What happens when there's not just x and y? What happens when there's a z value as well? So these dots could be sort of coming out at you at the page, and they have different heights now. So instead of having to group them in a circle, you now have to group them in a sphere. So they, instead of just having height, weight, they now have height, weight, and age. It makes it a bit harder to visualize what to group people with, because yes, you might have the girls or not necessarily girls. Again, you don't know. We might not necessarily know what these people are, because we could, in theory, have them, oops, not like that. We could have all of these be black dots, and we don't know what they are. So what that means is that we need to find a way to group them, and that is what this learning vector quantizer does. It doesn't necessarily say, hey, you go and find all the green dots, and you find all the red dots. It just says, find a group to represent. So let's, for example, now take that all of these dots are now black. We don't know what grouping they are. So again, what happens if, in theory, we now have a z-axis? So even though looking from top down, these four may look like they are grouped together, what happens if, again, if we say that this is the height and weight, what happens if all of these are also, some of them are younger? So these two dots here are like 10 years old. Meanwhile, these two dots here are also 10 years old, and all of the others are 30. Should we try and find a way to group the 10-year-olds that some are here and some are here? You could do that in a 3D space very easily, because there'd be a big vertical distance between them, which we can't really see here because it's a 2D image. But again, though, you can see in this example here, what happens if there's even more than 3 inputs? What happens if we have height, weight, age, and now also income? That we can't visualize. We cannot visualize a 4D space. However, what we can do is we can calculate distances or mathematical distances between these representative nodes, the square blocks, and these dots. And that is going to be very important, and you'll see why in just a second. So firstly, let's figure out how do we get these representative nodes onto these groups. Now, again, I'm going to use this very simple 2D example to illustrate what is happening, but pay attention to these inputs here at the bottom. Because again, this is most likely what will happen. You will have many inputs. So you'll have 4 possible inputs, and also again, 4 possible weights for those representative nodes. Now, the way we do this is essentially it's just calculating a bunch of distances. Now, I'm not going to bother you with the math because who cares about math? Again, it's just about the concepts. So in this case, we would calculate the distance between each of these inputs. So we would go one at a time. We would take this first input here that says 1100, just random inputs, right? And we would compare that to each of these nodes. And we might say, okay, well, you can see this one is maybe the closest, right? It has one value in common or something like that. And so let's say that hypothetically speaking, this bottom representative node is this one on the left here. And the input node is this one over here. What would that do? Well, what would then happen is, because this is closer than the other one, it would try and move it a bit closer. It said, well, since that one is the most similar to me, let me try and make it even more closer. And then what'll happen is we go through the next one. So let's say that hypothetically speaking, let me actually draw a bit. So let's say this second input over here, this 1000, we then calculate the distance between that and all of the other nodes. So let's say that hypothetically speaking, that second input node is that one over there, right? We calculate the distance between that and all of the nodes, the representative nodes. So we see that that is very far away from that second one, but it is a lot closer to that first one. And so because of that, what we do is we say, well, because it's closer to this first node here, let's shift it across, make it move a bit closer. So we'll take this node here and move it up. And also, I forgot to mention as well, but every time we update these representative nodes, so that was 2 shifts, these values at the bottom here would also be changed, the weights, because again, the weights correlate to where exactly those are. So if they initially started out at random places like the 0011, maybe after shifting them, they now become updated to have values like this. Let me just update them. They might now have values like this after being shifted once each. Now again, you would go through each and every one of these inputs and do this over and over and over and over again. And multiple times as well. Until eventually, what you'll have is at the end, one node will have magically moved across into the center of all of those points, and the other one would also move into the center of all of those other ones. But again, this is very easy to see and very simple in this 2D example because, I mean, obviously, what's the point of this, right? What is the point of this when we can easily see that if we have a new point, it's going to be similar to all of those? But again, the whole point of this is that we don't always have this ideal scenario of just 2 inputs. We might have many 4-dimensional, even more inputs, and it's not as easy to visualize then what happens. However, with these representative nodes, what happens is that after this grouping, where each node now is close and represents a group of inputs, because what happens if there's, instead of just 2, there are 5 groups and stuff like that. What we can then do is, if we ignore all of these other points, right? We now only look at these representative nodes. Let's say we now have a new input that we don't know of. Now, again, obviously, in a 2D space, what we would do is we can just visually see, well, which one is it closer to, and it is most likely part of that group. But again, in an unknown space where you have many different inputs that you can't really visualize, what you would then do is, again, it's all distances. You would calculate the distance to the nearest node, and whichever one is nearest, you would assign that input to whatever that group is. Exactly like you would do it in a normal 2D example, just we can't really see it anymore, right? It's the exact same concept of looking at it and seeing which is it closest to and assigning it to that group, but it's just done mathematically because we cannot physically perceive it. Hopefully, though, this is a good explanation. I apologize if it isn't. Again, I'm not qualified to teach learning vector quantizers in unsupervised learning, but hopefully, though, this helped at least somebody out there.